Hello, everybody. It's Friday on this side of the camera. Today we are going to do a lesson on this unit in particular. It's kind of like the cleanup of space, the last couple of things in astronomy. And we are really very close to being done with the entirety of our work for this semester. This unit's very short. There's only really two big lessons, and we're going to do a lab. So this upcoming week, you'll have this lecture. You'll have live class with me doing a lab, and then you'll have an async lesson on the Big Bang Theory. So this, again, still covering Standard 1. Standard 1 is astronomy. 1-2, that's more about the Big Bang Theory, showing how evidence has changed over time. The reason that standard is attached to this particular set of notes is because what we are looking at here is what evidence we have, and so sorry, and how we collect that evidence. How do we know what's out there? How do we collect the evidence? We've never been there. We can't travel there. We can't move at the speed of light. So how do we know what's out there? And that's what this is about. Construct an explanation to 1-3 using evidence about the life cycle of a star and what elements are produced. And this is a very chemistry driven concept here. There's one piece of technology in particular that we're going to talk about that chemistry teachers would love to learn about and get their hands on for sure. First one here is a satellite. We know what a satellite is. As a matter of fact, we've got lots of, we call it space trash or space junk out there, satellites that don't work anymore, and some that do. But satellites orbit Earth, and what they are is they're a carrier, right? They carry lots of different technologies. They may carry different telescopes, they may carry spectroscopes, and a lot of the other things, instruments that we're going to talk about today. But what they do is they provide data. So they send data about Earth, right? Talking about hurricanes and things like that. They also send data about what's happening in space, what's happening with distant stars. Telescopes are probably the most common piece of space technology. Optical telescope, optical being the eyeball, uses lenses, curved mirrors, or a combination of both to observe distant stars. So these could be as simple as the ones that you use in your backyard, or as complex as observatories in Iceland and in Hawaii. Um, others are used to observe distant stars and distant objects by their emissions. Okay, what are they giving off? And that gives us a lot of feedback. Again, getting more into that in just a minute with another piece of technology in particular, electromagnetic radiation. And that tells us a lot about the composition of a star, the life cycle of a star. Um, how it's forming, the distance. All right. So we get a lot of data just on what's being given off. A space probe, the rovers, you may have heard of those. Space probes are robotic things that we send out in space, right? We send them out because they need to go to places that it's not safe for humans to go, right? We are concerned with maintaining life and and so these robots allow us to gather data from Mars, for example, what you're seeing there. So samples of soil, different readings, pictures, and then other places. Other places maybe what's in the atmosphere and things like that. So it gives us data. These don't have to come back, um, but that data is absolutely essential to learning more about what's out there. Spectroscopy, spectroscope. This is the one I was really referring to when I'm talking about chemistry teachers, right? Spectroscopy is the study of distant objects based on what they're given off. Okay, what you see here is you see Roy G. Biv, and the concentration or the pattern of those frequencies of light that are being received from Earth. All right, so you're thinking of prism, think of white light, how it's broken into Roy G. Biv, and each one of those colors is not just a color, but it is a frequency of the wave that's being received by your eyeball or a piece of technology. I used to have these in my face-to-face classes, little boxes, and you look at different white light, incandescent, fluorescent. We looked at sunlight and it gives us this spectrum, this visible light spectrum. And those different concentrations tell us about the frequency of light that's coming off. They move at different nanometers. If I have, let's see, let me go ahead and pull that up. Frequency. Should have already had it pulled up. Sorry, guys. So nanometers, that's the frequency at which it is moving, the wavelength is moving. So we're moving at 380 to about 750 nanometers when we're discussing visible light, okay? And again, that's the range of red to violet. So distant stars, we can tell what they're made of based on that spectrum.
Our only contact with the distant stars is their light that's journeyed across the universe to reach us, and encoded in that light is the key to understanding what the universe is made of. And it's all down to a particular property of the chemical elements. You see, when you heat the elements, when you burn them, then they give off light, and each element gives off its own unique set of colours.
So I'm going to stop it right there because the rest of the video you can watch on your own. But each element gives off a unique set of light and a unique set of or concentration of that light. So what we're really talking about here is the electromagnetic spectrum. I told you guys we'd get back to this eventually. This is an entire spectrum of electromagnetic radiation from the very, very longest wavelength, um, the very, very most, or the least energy and the lowest frequency. We're talking about radio waves there. You can see that at the right end of this diagram here. Moving then more towards the left, and you'll see this diagram both directions, left to right, right to left, doesn't matter as much as the frequency or the energy down there at the bottom. And what you're seeing here is you're moving from that left to right. You got infrared just below red, and inside that little cutout right there, we have the visible light spectrum. And so we can tell the chemistry of distant objects, stars, and galaxies based on the concentration of these colors here. And each one looks different based on the elements that star or those galaxies or the nebula is being made of or is made up of. Above that, we have the UV radiation, X-ray radiation. You can see as we move down, these become more dangerous, right, to human beings. UV radiation, that can certainly cause cancer. It can cause sunburn, so definitely can present some issues for human beings. X-rays, of course. Why would you have an X-ray radio tech, whatever? Why do they put that big lined jacket over your body when they're X-raying a broken bone, say in your arm or your leg? And that's to protect your soft organs, because the radiation travels through those softer tissues. It actually bounces off the bones, which gives us the picture of the bones, but it travels through the softer organs, so you want to protect those organs. Why does the radio tech go behind a big barrier? Because distance and that barrier will protect from the X-ray radiation. Gamma is the highest energy, and the only thing that's going to save you from gamma radiation is to be far, far, far away from it. Okay, so definitely the most dangerous, highest frequency, and the most energy given off. Visible light, we can see this with the rainbow. You can see it with a prism. Those are the common things. This is the little piece of technology that I used in my face-to-face classroom right here, that spectroscope. So the light enters here. As a prism breaks it into different frequencies of light, and we can see the consistency right there. The right in the middle is the visible light spectrum of the electromagnetic spectrum, and this is the range that human eye can see. Roy G. Biv, you've heard of that. There was talk at one time about actually removing indigo. I don't know if they actually followed through with that. I don't think they did, but that'd be weird. Roy G. Biv. But the composition of distant stars can be determined by the spectroscope, not this rudimentary one that I used in my classroom, like serious high-tech spectroscopes, okay? But you can see down here each element, and I had several of these cool lights that were, they had to be like 20 years old. But we set up these different lights in my classroom, argon and neon, and yes, mercury. I know that that will turn a couple of eyes saying that, but we did find them, and it was super cool. But we got to look at um, those different elements and the light that they produce. And so my students got to color in the various frequencies using that little piece of technology there that they saw. And so each element, again, has its own pattern. All right. Essential takeaways. You need to know the relationship between wavelength, energy, frequency, and danger. Okay. So more energy, higher frequency, closer wavelength, more danger. All right. Lower energy on the right hand side of that spectrum there that you're looking at. Lower energy, longer wavelength, lower frequency, less danger. So you need to be able to know that. Space is a vacuum. Why is this important to what we're talking about with space? Because space is a vacuum, so light can travel. Light travels at the same speed, the speed of light, which is incredibly faster than the speed of sound. I think let's see, let's Google that real fast. The speed of sound is like speed of sound. Yeah, 343 meters per second. 343 meters per second. The speed of light is like million, if I'm not mistaken. Yeah, 300 million meters per second. So that's a big difference. 300 meters per second or 300 million meters per second. So light's booking it. It's moving. It's the fastest thing we know. We figure out how to travel at the speed of light. We may figure out how to travel in space. Why do we need to know this? Again, this is how we read or get information about distant stars, distant galaxies, distant nebulas. What is being given off? What is that light telling us? The light that's emitted, picked up by spectroscopes that are often mounted on our satellites in space. It can determine the makeup of distant stars. So the frequencies that are produced, the colors that we're picking up, colors, remember, equal frequencies, um, that tells us what the elemental makeup of distant stars are. So it gives us the vast amount of data that we have about distant stars is it comes from these pieces of technology. And I don't know what's happening with my Nearpod here, but I think that was it. Yeah. All right. So big takeaways without. Oh, there we go. Beautiful. This is the periodic table of elements and what we would receive if distant stars are giving off these elements. All right. So here's some elements. There's iron, there's hydrogen, helium. I was really hoping Miss Howell was going to be able to teach this lesson because I thought this would be really cool to get from a chemistry teacher, but she's out on maternity leave. But we have oxygen and nitrogen. We have sodium, magnesium, aluminum, um, potassium there, calcium. All of these elements give off different frequencies of light. And so if we can match up the frequency that we see that we're getting, the data that we're getting in our spectroscopes to these patterns, then we know what the makeup of that star is, what the compositional makeup of that star is. And again, so going back to the very beginning here, why do we study this? Why is it important? Oh, well, let's go to that. That's perfect. Why is it important? Um, how do we know what distant stars are made of? Okay. How do we know? What kind of information if we can't go there? We're not Miss Frizzle. We can't load up on the Magic School Bus and travel there. We don't have that technological capability yet. So how do we know? How do we have this understanding of the composition of distant stars, distant galaxies, distant nebulas? Okay, and the answer is these wonderful things called spectroscopes, other pieces of technology like telescopes and then also probes and as well as satellites, which are our carrying um, technologies. They carry up this information or they carry up these other technologies with it. Okay. So this I would screenshot. If you're my student, make sure that you screenshot this because this is a really good opportunity for you to have a little bit of study guide for the Unit 6 test. Okay, so the next lesson that we're going to do is async, and it is on stars, galaxies, and the Big Bang Theory. Please make sure that you get that accomplished, my students, before your Wednesday, Thursday classes because we're doing that lab. All right. Thanks, guys. Thank you for your attention. See you in class.